Okay, this week we're talking about soil chemical properties. So the soil solution is soil water, and there are nutrients and other chemicals in the soil solution, and if these nutrients remained in the solution, they could all be quickly lost from the soil. So adsorption is the ability for an object to attract and hold on to particles on its surface, and so the solid particles in soil have this ability to adsorb, and that would be water and other nutrients and other chemicals. And the most important adsorbers in soils are clays and organic matter. The smallest particles of humus and clay in the soil are soil colloids. They're very active, and so the clay is going to be the inorganic form of soil colloids, while the organic matter as humus is going to be the organic version of the soil colloid, and they attract ions. They may be exchanged, and you can see here we've got cations attracted to these particles. So ions are atoms or molecules that have a net electric charge, and this is due to a loss or gain of one or more electrons. A cation is positively charged and anion is negatively charged. So generally speaking, we're dealing with negatively charged clay and organic matter. This is in our types of soils, and if you notice in your reading, it's going to talk about tropical soils having a positive charge, but we're going to focus on the negatively charged clay and organic matter. So they attract positively charged ions, they repel negatively charged ions. And cation exchange capacity is the capacity to hold on to cations, measured in milliequivalents per 100 grams or centimole positive charge per kilogram, and that's the newer version of measurement, and we'll see that in a second. So CEC varies with the percentage of clay, type of clay, pH, and the amount of organic matter. And this is just to show you that sands have a low CEC range, whereas organic soils and clays have a much higher CEC range. So just so you can see what cations and anions in the soil might look like, ammonium is the form that would be taken up by the plant in nitrogen. Nitrate tends to leach because it's negatively charged and it will not adsorb onto the soil colloids. So soil clays are stacked in layers, there's a slight separation, they're negatively charged, and they have to be balanced by cations. So here's some of the cation retention on soil clays. pH is important too, because if you look at this low pH on the left, only hydrogen's being retained, and really what you want are to retain some of the nutrients. So you definitely need to increase the pH if you want more nutrients available to the plants. Nitrate is an anion, and it can leach from precipitation or overwatering. The ammonium form, nitrogen, is the cation, and that would be adsorbed on our negatively charged soil colloids. Okay, so here's the graphic on this. So we've got a clay particle that's negatively charged. It binds cations. And then number 2, you can see the cations are exchanged. So that's what cation exchange capacity is. So hydrogen ions are obtained from carbonic acid or from the plant itself, and they displace the other cations attached to the soil particle, so they can go into soil solution and be taken up by the plant. And not all clays are equal in their ability to have a surface charge. Kaolinite has very low activity clay. That's what's used for pottery and that sort of thing. You can see humus has a very high CEC charge. So the basic structural units for clay minerals are silicon tetrahedron and aluminum octahedron. So in a 1-to-1 clay mineral, they have one sheet that's tetrahedral and one sheet that's octahedral. So 1-to-1. And with the 2-to-1, these are going to be different combinations, and these are the type of, because there's enough space between these things, there's space for cation exchange capacity to happen. So kaolinite tends to curl. It doesn't expand with moisture. It's got a variable charge, tends to be low CEC. It's non-sticky. So hydrogen bonds are in the interlayer space is what I was talking about, and those are very strong, and so it's very difficult for any exchange to occur. So here's the kaolinite 1-to-1 type clay. Okay, here's a 2-to-1 type clay. It expands easily. It's got a high surface area, able to retain a lot of nutrients, very sticky. This is the kind of clay that we think of when we think of clay textures. Okay, so soil pH I mentioned. Soil pH is very important when you talk about plant access to nutrients. It's the power of hydrogen. And so acidity or alkalinity is determined by hydrogen or hydroxyl ions in the soil. So when the hydrogen ions outnumber hydroxyl ions, the soil is acidic, and the reverse condition is basic. So the productive range for plants is between 5 to 7.5. And I love this graphic because it's really effective. So the leg that's sticking out of the graphic here is hair remover, and that's got a very high pH. That's about 12. And then you go down to, say, tomatoes. That's 4. Vinegar is 3. And you can see typical rainwater is actually between 5 and 6. It is not neutral. So irrigation water is very important when you're talking about pH. And humid areas tend to have acidic soils. Arid areas tend to have alkaline soils. Parent material, if you've got high calcium, it may result in a high pH. High sulfur may result in low pH. And you're usually managing with fertilizers and other means. So phosphorus is most available to plants at 6.0 and 7.0. Aluminum becomes actually toxic in very acidic soil, and iron and manganese are more available to plants in acidic soils. So you've probably seen this graphic before, but what I want you to look at is between 6 and 7, just follow this down. You see nitrogen's broad, phosphorus is broad, potassium, calcium. You're going to have the most nutrients available to you in that 6 to 7 range. Iron, copper, zinc, manganese, those are going to be more available in very acidic soils, and boron, etc., are going to be more available in higher pHs. Soil organisms tend to prefer neutral or near neutral soils, so fungi are more tolerant of acidic soils. So the thing to note is that the more diversity you have in the soil, the healthier it will be. But soil pH should be checked once every 3 years, or if you see problems arise. So soil pH and nutrient availability, biological activity and processes determine the abundance of soil organisms, determine which plant species will grow. Low soil pH slows the biological transformation of ammonium to nitrate. Physically, indirectly, high pH can disrupt soil structure or aggregation. And so this is just an example of an iron deficiency on rhododendron. They prefer a range of 4.5 to 6. Chances are you have this next to a lawn, and you're keeping the lawn covered with calcium regularly, and so that raises the pH, and that inhibits the iron take up by the plant. And here's a deficiency on grapevine, magnesium deficiency. So pH is pretty important. So soil pH and the secondary micronutrients solubility of compounds, nutrient availability, cations on exchange sites, common deficiencies in acid soils, calcium, magnesium, sulfur, and molybdenum. Common deficiency in alkaline soils are going to be boron, copper, iron, manganese, and zinc.